All right. So, again I am going to continue with my tutorial questions. So, if you remember that in the last tutorial we discussed mainly how to calculate entropy for using combinatorial ideas, and specifically we discussed this interesting problem of finding the entropy of a set of charges that are stuck to the corners of a cube. So, but now we change tracks a bit, and I am going to now start discussing more physically realistic systems. So, those discrete combinatorial examples are just toy models, and they are useful for driving home the concept of what entropy is. But it really does not help you understand the real world, because the real world is not made of very simplistic finite systems like that. So, specifically in this tutorial I am going to take an example which is quite realistic, and that is of a classical ideal gas. It is ideal in the sense that it does not interact with the molecules, do not interact with each other, but they interact with externally applied fields. So, specifically I am thinking of what is known as a harmonic trap. So, in other words, so think of just intuitively you can think of each atom to be connected by some kind of an imaginary spring to the origin. So, each atom is connected to a spring which prevents it from, so it can kind of go round and round like this. I mean, it can do anything it wants, but there is a cost to running away from the origin. So, and that cost is basically given by Hooke's law, and so you see that it is basically this is the force. So, if Ri is the distance from the origin, there is a restoring force which is proportional to Ri and in the direction of that. So, that is effectively what this model is. But you might be wondering, why is this realistic? Because it involves connecting subatomic particles to springs, but then the spring is really a metaphor. It is a figure of speech for a potential that goes through a minimum. So, in other words, you know that any function that has a minimum can be Taylor series expanded around the minimum, and the leading term. So, there is the leading term is the constant, and the next leading term is going to be proportional to x squared, where x is the, so f of x, if it goes through a minimum at x equal to 0, you can always write it as f of 0 plus something positive times x squared, and that positive you can identify with 1/2 k, where k is the effective spring constant. So, any potential that goes through a minimum can be thought of as due to a spring. So, I mean that's so in other words it's just an analogy, and so the spring is a metaphor for a potential that goes through a minimum. And practically these harmonic traps nowadays are quite commonly achieved in the context of cold atoms, where these traps are typically the crisscrossed laser beams that so the region where the laser beams crisscross is the place where the atoms get trapped through in this harmonic potential. So, this is the Hamiltonian of such a system. So, if you have n atoms, and okay, this is up to n only. So, you have okay, n minus 1. So, you have n atoms, and so the point is that so there is a kinetic energy, and then Ri. So, Ri squared is basically xi squared plus yi squared plus zi squared. Okay. Okay. So, xi squared plus yi squared plus zi squared. So, that is Ri squared. So, so the idea is to answer all these questions that follow. So, the first question says that show that the angular momentum vector is a conserved quantity. Okay. So, I have to show that there is a conserved quantity. Then if the gas is rotating with some angular velocity, So, I have to show that the probability of being in a certain volume in the phase space is can be thought of as this. So, when if it's not rotating, this is absent. So, it's just e raised to minus beta h by z. So, that is the canonical partition function. So, when it's rotating with an angular velocity omega, so there is going to be an additional energy associated with the rotation. So, you just think of your classical mechanics where you have this the description of dynamical systems in a non-inertial reference frame. So, that is where this comes from. So, basically the energy is going to be the angular momentum times the angular velocity of the non-inertial reference frame. So, so the idea is to find the partition function by imposing the condition that the total volume in phase space is conserved and it is normalized to 1. Alright, so so the third question is find the average of the so if omega is in the z direction, so the idea is to idea is to find the average of the angular momentum vector in the z direction, and then also the goal is to find the average of the squares of the coordinates themselves. So, these are the questions that we want to answer, and let us get to it. Okay, so let us first try and answer the first question, and which is this, and that is show that the angular momentum is conserved. That is fairly obvious, but I am going to do it. So, Li is nothing but Ri cross Pi. So, so notice that there is a classical mechanics problem. So, so regardless, we can always, even if it is quantum mechanics, this is still true. So, I can write this as dpi by dt plus dri by dt cross pi. So, this is velocity, and velocity is parallel to momentum because there is no magnetic field and all that. So, at that level there is nothing there. So, so this is 0 and this is nothing but the force. So, that is force applied. So, remember I told you the force is the given by Hooke's law, which is basically a restoring force, where the force is proportional to the distance vector and in the negative direction. So, this is therefore 0 because it is a central force. So, as a result, the angular momentum of the particles is conserved, well, in the absence of rotation for this Hamiltonian, that is. So, the idea is that if it is rotating, you can move to the non-inertial reference frame, and then you will pick up a certain rotational energy which is in excess of this Hamiltonian given by omega dot L, which gets added on to the Hamiltonian, and this is going to be your phase space. This is the probability of finding a particle, well, it is the probability of finding a ith particle in a volume d cubed Ri and d cubed Pi in the phase space. So, you know what phase space is. It is just a collection of 3 coordinates, spatial coordinates, and 3 components of the momentum, and there are n such particles. So, it is basically a 3n dimensional, well, it is actually 6n dimensional because x and p are also there. So, there is 2 times 3 times n, so which is a 6n dimensional phase space. So, we successfully solved the first part, which is very easy. It is fairly obvious. It is to show that the angular momentum of each particle is conserved if it is a Hamiltonian of this type, and this is pretty evident, self-evident, because it is a central force. Okay, so part B says if this is your probability distribution in phase space, find the partition function. So, we are going to use this idea that the total probability is conserved, and then what we are called upon to do is called upon to evaluate this integral, which is so we have to calculate this basically. This is what that is. So, this is going to be clearly the answer for one particle raised to n, okay, because that is how it is going to be, because they all decouple. So, the particles do not talk to each other, they just interact with external fields, and omega is uniform. So, that means omega is the same for all the particles. So, it is just one, the partition function for one particle raised to nth power. So, the question is, how do you calculate the partition function for one of the particles, and that is going to be d cubed pi d cubed ri over h cubed times e raised to minus beta times pi squared by 2m plus k by 2 ri squared times e raised to beta. And remember that we have chosen omega to be in the z direction. So, it is going to be Liz, and what is Liz? It is xi pyi minus yi, this is Lz pxi. So, now I am called upon to evaluate this integral. So, it is Ri squared. Okay. So, so the question is, how do you do this? So, the way you do this, of course, is to make use of the fact that so you might be thinking that well, let us try spherical coordinates because there is Ri there, but then the spherical symmetry is spoiled by this term. So, it is not a good idea. So, what we should do is basically write Ri as xi squared plus yi squared plus zi squared, and then just use Cartesian coordinates. So, I am going to do it that way, and you see, so this is going to be dpx, dpy, dpz. So, I am just writing it out fully. So, I really want to take this opportunity to display all the steps, so that those of you who are inexperienced in doing these calculations will benefit. Those of you who already have an idea about how to proceed will probably feel impatient. So, you should just feel free to fast forward and do it on your own, or just close this and do it on your own. Just take it up as a challenge and do it on your own. Okay, so so how does this work? So, so it is going to look like this. So, it is beta k by 2 xi squared plus minus beta omega xi p by I minus yi pxi. So, this is I mean, I am going to have to evaluate this integration. So, I am going to do this first, and then remember that there is a e raised to minus beta pi squared by 2m outside, which I have to do later. So, now let me try and do this. So, it is very easy to, so remember that if when I try to do the z, it is easy because there is no z anywhere else. So, the z integration is going to be easy. Okay, so so what is the z integration? Zi. So, remember that the components can be positive or negative, and there is no restriction. And remember, this is classical mechanics. So, momentum and position, the phase space has meaning, right. So, I have integrated over position and momentum. So, that means the particle can have a well defined position and momentum at the same time. So, all we have to do is calculate this result for, so that we will be done with one of the integrations. And so remember the standard formula that if you have e raised to minus a x squared dx, and this is nothing but square root of pi over a. Okay. So, yeah, so this is square root of pi over a. Okay, so that is what that is. So, well, you can either look this up, or this is very standard integration. So, I am going to write this as square root of 2 pi over beta k. So, this is the answer for that. So, now I have to do the other things. So, that means I have to do the x integration. The x integration is slightly more complicated because there is a quadratic term, but there is also a linear term. So, there is a standard way of handling this, and that is called completing the square. So, for example, suppose I want to do the x integration, what I am being called upon to do is this integral. Okay. So, this is the integration so I am being called upon to do this. So, the way I am going to do this is I am going to do what is called completing the square. So, I am going to rewrite beta kappa by 2 xi squared minus beta omega pyi xi. So, I am going to rewrite this as, so I am going to take this common factor. Okay, let me do that right here. So, I am going to put a bracket here, but then I will have to divide by beta kappa. So, the beta cancels out, that is what that is. Okay. So, now this quantity just in the brackets is nothing but xi plus omega by kappa pyi whole squared minus omega squared by kappa squared pyi squared, that is what that is. So, there is a cross term. So, there is a x squared and there is a cross term which is this, then there is the term which is quadratic and py which is not present here. So, I have to subtract it out. So, so that is what that is. So, that is called completing the square. So, in other words, the integration over the x part is going to be simple, because now it is simple because earlier it was this. So, now after completing the square, it is going to so, it is going to be that times the integration over the term which is simple quadratic. So, this xi is just shifted by a constant. So, as far as the integration over x is concerned, pyi is a constant. So, I might as well call xi plus omega by kappa pyi as x dash I, and then I integrate over. So, dxi is same as dxi dash, and then I integrate over dxi, and I end up getting this result which is 2 pi times beta kappa. Okay. So, this is what I get when I complete the square, and same thing when I do the y integration. So, now I am done with the x, y and z integration. So, I am going to collect all this together, and let me display that after collecting them all together. Okay. So, let us go to the next slide. Okay. So, the p integration still remains, okay, but the x integration is done, and so the x integration is done, and what was the answer? I just have to collect them all together. So, remember that I did the so when I do the z integration, I get this. So, when I do the z integration, I get this, when I do the x integration, I get this. Then it stands to reason that because x and y are similar, because remember there's a inhomogeneous term or the linear term in x, and there's a linear term in y as well due to the non-inertial reference frame, but there's no such term for the z. So, for the z the answer is very simple, it's this, but for the x and y it's going to be similar to this. So, for the x integration we got a yi squared, for the y integration we are going to get a p xi squared. Okay. So, I am going to use that. So, this is going to look like e raised to beta omega squared over 2 k pyi squared times square root of 2 pi over beta k. Okay. So, I am going to collect that here. So, it is beta omega squared plus pxi squared. Okay. So, that is going to be that result. So, this is because of x integration, this is because of y integration, and then there is 2 pi over beta k, because there is a square root and 3 of them, this. So, x, y, z. So, that is what that is. So, now I am now being called upon to evaluate this quantity. So, now it is easy. So, so again remember that what is pi squared? Pi squared is nothing but pxi squared plus pyi squared plus pzi squared. So, I am going to rewrite this as pzi over, well, 1 by h cubed is outside, okay. So, there is that, then there is this, and finally, there is the rest of it. I mean, the rest of it is simple, it is beta kappa raised to 3 halves. Okay. So, now how does this work? This is very easy. So, basically it's just well, we have to make sure that the angular momentum is not too high, because otherwise this diverges. Okay. So, so if I integrate over pzi, this is going to look like 2 pi sorry, it is pi over square root of a. So, that a is basically beta over 2 m. So, it is beta over 2 m, and similarly here. So, this constant also tags along. So, this one and this one together, this is this is this. So, I have to calculate this, but this is the same thing twice over. So, so what is the coefficient here? So, it is again square root of pi by a whole squared, and what is a here? A is nothing but you know, it is beta over 2 m minus beta omega squared over 2 kappa. So, that is what a is. So, that is the answer. Okay. So, that is the partition function for one particle. So, let me write that out properly. So, if I write this out properly, it is going to look like 1 over h cubed times 2 m pi over beta raised to 1 half times 2 pi over beta kappa raised to 3 halves times pi over a, which is beta over 2m minus beta omega squared over 2 kappa. Okay, so this is the answer for the partition function for one of the particles, and for n particles it's this raised to n. So this is the canonical partition function. So let's try and see what are the other questions that have been asked. So we answered. So they asked us to find the canonical partition function. We just did. So it's one. We found it for one particle. Now for n particles, you raise it to nth power. So the next thing we have to find is the average angular momentum. So that's easy because so remember that z is basically it's this integration Lz times e raised to minus beta h. So so if I take dz by d beta omega and put a minus sign, I will get an Lz downstairs, and then I divide by z. So this is basically my expectation value of Lz. So so it's basically ln. So this is nothing but minus d by d beta omega ln z. So I just have to differentiate ln z with respect to beta omega and put a minus sign. So that's my average value of Lz. So let's do that. So let me do that right here, because otherwise I have to flip the slide. So z is nothing but z1 raised to n, and ln z is n times ln this. So notice that I am going to think of beta omega as beta times omega. So I am differentiating with respect to omega and then multiplying by beta. So basically I have to differentiate with respect to beta. So for that purpose this is irrelevant. So so if I take log, I will get a whole bunch of things which do not depend on omega. So I only have to worry about things which do depend on omega. So I am going to even ignore this pi there. So it dimensionally does not make sense, but since I am only interested in the derivative with respect to omega, it is okay. So 2m minus beta omega squared over 2 kappa. So now if I take the derivative with respect to omega, I get so well, I have to differentiate this and then I get minus beta omega over kappa. Okay. Then I put a minus sign and I put a 1 by beta. So then I get rid of this. So this is my L of z average. Okay. So it is going to be proportional to omega for small omega. So you can see that for small omega. So if there is no, if the gas is not rotating, then the average angular momentum is 0. If it is rotating, for small omega, it is going to be equal to proportional to omega. Okay, so I am going to allow you to think about what happens if omega becomes too large. Then there is something funny that is going to happen. So I am going to ask you to think about what is they haven't asked you in this question to think about that. So but I am going to ask you to think about it. So obviously something funny is going on here. So they should have asked that question. They haven't asked. So but you should think about it. So the other question they have asked is find the average of x squared, y squared and z squared. Well, we expect the average of x squared and y squared to be equal, but not equal to z squared, okay, because of the nature of the way it is. So I have to calculate the average of z squared separately and average of x squared separately. But there is a nice symmetry that we can exploit, and that is okay, we could exploit if we knew how to do the other p quantity. So I might have to do it explicitly. Alright, so let's do it anyway. So how do I calculate the average of x squared? So So, suppose I want to calculate the average of x squared. So, I have to calculate basically z times dxi. So, there is a xi squared there, and there is a dy dz, okay, and there is a dpi dpix dpiy dpiz, then there is a e raised to beta p squared by 2m plus k ri squared by 2 minus beta omega lz. Okay, so you'll have to excuse this long expression. So, where this z is the usual canonical partition function without this xi squared. So, z is whatever it is without the xi squared there. So, the question is, how do I deal with this? So, it is very similar to what we did here, except that so we have to kind of postpone integrating over you know xi squared. We kind of integrated over xi, so we should be doing the p integrations first. So, so let us do this, because I mean it is going to be not so easy to borrow from the earlier result. So, it is going to look like this. So, I am going to first do the p integration. So, if I do the p integration, how does it look like? So, the first integration is the one which does not have which has only pz. So, pzi 2m, okay. So, there is pzi, so integrated over all the p's. So, this is just going to be square root of 2m pi by beta. Okay, so that is the z integration. So, the other pz integration. So, then you need to do the px integration, but then px has this linear term as well. So, you have to deal with that. Beta pxi squared by 2m times e raised to beta omega yi pxi dpxi. Well, this is not a ratio, it's the next calculation. So, so again you have to complete the square and rewrite this in that fashion. So, I am going to rewrite this as e raised to minus beta over 2m, then this becomes pxi squared plus or minus 2m omega yi pxi, okay. So, dpxi. So, this is going to be so pxi minus m omega yi whole squared is going to be this, and then see, this is the completing square. So, if I square this, I get these two terms, but also I get something which is not there, which is the square of vi. So, I have to cancel that out later on. So, in other words, I am going to have to rewrite that as beta over 2m times m squared omega squared by I squared. So, now I have to calculate this, and that is nothing but square root of pi 2m pi over beta, and then I am left with this. So, this is all, this was already there. So, it is 2 times m omega squared by I squared. So, so same with the rest of it, I mean the last one. So, you have pyi squared by 2m times e raised to minus now beta omega xi pyi dpyi and this is regardless of, because it depends on omega squared, does not matter whether it is plus or minus. So, I get beta times beta over 2 m omega squared xi squared. Okay, so that is what I get when I integrate over all the p's. So, so now I am forced to reckon with x integrations. The x integrations are going to depend upon, so there is an xi squared there, but there is not any xi squared here. So, I will have to deal with that. So, I am going to see if look at it here. So, if I integrate out the yi and the zi, so long as the xi does not mix with the yi and zi, I am safe. So, in fact it does not, you see, there is no term which has xi times yi or xi times zi. So, I might as well ignore this, I might as well not perform the yi and zi integrations, because they are going to cancel out coming from here. So, the zi, so you will have to think about it. So, if you do not like all these shortcuts, you will have to do it yourself and convince yourself that you can. Basically, the shortcut I am recommending is that you do not do the zi integration or the yi integration, because the same thing comes in the denominator, and xi does not couple, because the xi is special, because there is an xi squared in the numerator, but there is not any in the denominator, and so long as xi does not couple to yi or zi, the yi and zi integrations are going to cancel out from the numerator and the denominator. So, you might as well not do it. So, all you have to do is do the xi integrations and be done with it. So, that is what I am going to do now, and in order to do that, so I am going to use this and the xi part of that. Okay. So, so I am going to go to the next slide and write it that way. So, my xi squared therefore is nothing but integral dxi xi squared times e raised to beta. So, that comes from there, and there is this term, and that is all, and then I am done, because I do not have anything else. Beta by 2 m e raised to beta by 2 m omega squared xi squared. So, that is all there is to it, then without the xi. So, this is the average of xi squared. So, the question is, how do you do this? As usual, let me call this something, call this something, call it some j or something. So, this j is has the form e raised to lambda xi squared, and so as far as this is concerned, so I can write xi squared average as, just take the lambda derivative of ln j, and you are done. So, all I have to do is calculate j. So, this is nothing but pi by lambda. So, the lambda derivative of ln j, so the ln j is going to be some constant minus 1/2 lambda ln lambda plus some constant. Okay. So, the derivative of ln j with respect to lambda is basically minus 1/2 by lambda. So, this is minus 1/2 times minus 1 by 2 lambda, and so as a result the average. So, what is lambda here? So, lambda is nothing but so minus 1 by 2 lambda becomes this is going to look like 1 over beta kappa minus beta m omega squared. So, it is going to be 1 over beta into kappa minus m omega squared. So, that is what this is. So, we better make sure that it is dimensionally correct at least. So, you see m omega squared. So, beta is dimensions of inverse energy and kappa is the spring constant which has dimensions of m omega squared, and if I take this here, so I get length squared times m omega squared. So, it is going to be x squared times omega squared, which is speed, and m times speed squared is energy. So, that is dimensionally correct. So, that is one way of checking. After a long calculation, it is really disappointing if things do not match dimensionally. That is a surefire indication that you have gone wrong somewhere, and that is an easy way of checking the correctness of your calculation. But then do not wait until you have reached the very end. So, it is in fact what I did is not advisable. So, if you are inexperienced, you should periodically check your dimensions in at the intermediate steps as well. So, then this is as far as x is concerned, because x and y are similar, this is the same as far as x and y are concerned. Okay. So, it is the same answer, but only thing is now the z is not the same answer as this. That is because the z is different. Okay. So, now if it is z, so there is no see, remember there is no z anywhere else. You do not have to worry about any of this. So, it is the z squared is as simple as zi squared e raised to beta kappa by 2 zi squared divided by okay. So, no, it is the same thing. It's just like this with respect to lambda. Okay. Well, this is actually minus lambda here. Okay, so I should have put a mod lambda there. The lambda is actually the other side. Sorry, I got the sign wrong. Okay, so it's going to be this sign. Okay, so it's going to be the other sign. Okay, so here it's going to be exactly this. Okay. So, differentiating ln j with respect to lambda gave me minus 1 over 2 lambda. So, so that is what that is. So, it is minus 1 over 2. Well, it is actually sorry, it actually becomes plus here. There is a, so I made mistakes twice. So, it is basically, see, it is the ln j is nothing but it is lambda raised to minus 1/2. So, ln of that. So, it is minus 1/2 ln of lambda. Okay. Yeah, so that was correct. So, now I am going to have to calculate this as 1 over 2 lambda, and this is my lambda. So, so it is going to be 1 over minus beta kappa over 2. So, so this is going to look like 1 over beta kappa. Okay. So, sorry, this was plus then. Okay. So, that makes sense now. So, it has to when omega is 0, they have to be all equal. Okay. So, I am sorry for the sloppiness, but so if you do it properly, you will get this. So, so now let me summarize. Average value of x squared is same as average value of y squared, which is same as 1 over beta times kappa minus m omega squared, and whereas the average value of zi squared is as if there is no omega. Okay. So, yeah, now it makes sense. Okay. So, that answers all the questions that are asked here, and So, you can see that some of these calculations can be a little tedious, even though it is straightforward, but unless you do it yourself. So, and one of the highlights of the calculations that I have shown you here is that I have done everything by hand. I have not used any computer or any software. In fact, that is also not advisable. So, nowadays you have software which does all this. So, it's actually a waste of effort and waste of time to do it this way. So, it's better for you to learn some software, some symbolic algebra packages like Mathematica, and you just type in your integrals there and you get the answer. So, I am going to stop here and continue with my tutorial questions in the next hour.